Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today I'm going to continue this part on data models. But before we do, I would like to see if there are any follow-up questions on HBase, on anything that wasn't clear or that I could re-explain in a different manner. Yes? Oh, yes, I can certainly adjust. That gives you more time to think if you have a question. That should be, is it better? Yeah, awesome. So any questions? Or on Zoom? Don't see any Zoom chats. Okay. So then maybe I can just say a few words about the follow-up questions of yesterday. I sent a message on the forum for everybody to see. I think there were 3 open ones. One was about the cache of HBase and the resource consumption. And the short answer is that it can cause trouble to other people. So basically, there are people with very heavy queries that are disk I/O bound. And for these, the memory and the CPU would be secondary, so the trouble it causes. But other people who are also using HBase at the same time might have more lightweight queries, less disk intensive, and then it could slow down their queries because the cache keeps adding and evicting blocks, right? So then you can deactivate it. There is a way when you have your query, per query, you can say, don't use the cache for this query, and then this avoids it, right? If you know that your query doesn't need caching. For whom is this one clear? Right, very good. Then there was another question on why US East 1 is very popular. That's Virginia. There's many reasons actually that I found. It has low taxes, it has low electricity prices. There's not so many natural disasters there, so it's the data loss is even less likely. It's close to Washington, D.C., so there's all the government that uses the resources. It was also very early a component of ARPANET and then Internet, so it had a lot of optic fiber infrastructure from very early that was already pre-existing. And then, of course, since everybody is there, then everybody wants to be there too, right? Because then you can have your computer resources next to the other companies that also have computer resources, and then you have very low latency talking with other companies. And so that is a reason why people, even outside the US, might still have an interest in having some resources there, right? So that's the short answer. For whom is that one clear? Right, okay. So now if you hear about data centers in Northern Virginia, then you know why. And the third one was about, I don't remember, which was the third one? It wasn't about the blocks, it was about, does anybody remember? Yes? Yes, thank you, the meta table, right? So yes, the last one was why the meta table is not handled by the H master and why it has to be one of the region servers. And here I would say the short answer is availability and resilience. You basically have different single points of failures. You don't have everything on the H master. So if the H master goes down, you don't need to worry about the meta table. And also availability, because when the H master is down, the clients can still speak with the region server that handles the meta table. And there is yet another reason is that the meta table is a table like any other, so it has H files and so on, communicates with HDFS. And so it has an advantage if we are on the same machine as the data node because we can short circuits. So that's yet another reason, right? For whom does that make sense? Right, okay. Still any other question? Give you a last chance. Yes?
Given that on Monday, AWS fell down, does this affect the amount of nines they can advertise in the 11 nines of consistency, resilience, or whatever, or this doesn't affect them?
So that's a good question. So first, maybe I will repeat over the microphone. First, there is no such thing as a silly question. That doesn't exist because we are in a university and we're here to learn. So it's about the legal aspects of the service level agreement of Amazon with all the nines, right? 99.99999 of availability, if that affects it. The short answer is I don't know, but my guesses are that you need to consider that it was the DNS that was at fault and not the system by itself. So maybe that plays a role in the legal agreements, because technically you could still connect to the servers if you knew their IP address, right? That was still working. Now I don't know who was responsible for the DNS, right? Because the DNS is distributed over the world, right? There's a whole hierarchy of DNS servers. Amazon is one, also has DNS servers. So I don't know if they had a problem with their own servers or if it was something else. So now you can see why lawyers are needed, right, for that kind of things, because so maybe we'll know about this just like we did for when the data center caught fire in eastern France a while ago. Maybe in a few months we'll know about this once they have figured out the implications for the service level agreements. Right? Thank you. Other questions? Let me check on Zoom too, and otherwise I'll continue. And Zoom seems quiet. Lots of people on Zoom, but very quiet. You can hear me, right, on Zoom? Yes, I have a confirmation. Okay. So I will now continue with data models. First, a wrap-up. So there is this overview to make sure that you have all of the concepts where you see that if you look at all levels, so eventually everything is made of zeros and ones, right? When you have either as a file or as an object or as a value in HBase, it's just bytes. So you need to read or decode it, whatever the encoding is, to text, which is the syntax. But of course, it assumes the file is not corrupt, that you can decode it successfully. Then, if it is well-formed, remember that's the word for whether you can parse it or not, as JSON or XML. If it is well-formed, you can parse it. What you get is a memory representation that's typically made with Java classes and objects. If you use Java, right, you're going to have Java objects that have pointers to each other. And that's called in XML the info set, information set. You could consider that there's a JSON info set, but as I said, this one is implicit because many people just assume that the syntax is self-explaining, which is not quite true, but as a first level, you could assume that. So that's what we call an info set. And then, and this is what we are studying in this course, if it is valid against a schema, then we can annotate it, which means that we slightly transform the memory representation with more accurate type information. For example, if you parse it as JSON, you would get a string for a foo, right? 2025-10-22. But if your schema says a date is expected, then you are going to replace that string. When you annotate it, you're going to replace it with an actual Java time, date time object, right? It's no longer going to be a string. It's going to be a specific Java object of the specific class that handles dates, right? For whom does that make sense? Right? Okay, so this is, you see, the whole architecture. And it's very precise, especially in an enterprise environment where you deal with a lot of data. It's very important to be very precise. And I even have a meme for you, if you want to see the idea of what I'm saying here, is that if you're just prototyping with a new project, it's totally fine to take shortcuts, right? You take a string, you just grep it, and that's and you find what you're looking for. For a prototype, maybe that works. Even better is, of course, if you write something that cleanly parses it to a dict. So if it's a serialized object, that would be a Python dict. Then, of course, instead of writing an ad hoc script that's going to parse something, you can also use a library like Antelar or Bison that allows you to write a proper grammar, and then it generates the code that parses it, right? Whoever used these things, right? I assume in compiler design too, you saw these kind of things. And then, of course, you can just do import JSON, JSON.parse, right? And just use an existing library. But if you are in an enterprise environment or a part of standardization committees and so on, if you really, really want to do things cleanly, then everything starts with a specification of a data model. what are the first-class citizens in your data model? For example, object, arrays, and atomic values could be your first-class citizens. You need a mapping from the syntax to an instance of the data model saying for what syntax do you get what. That might be an N-to-1 mapping, right? You might have multiple documents that leads to the same representation. For example, you might have documents that have the keys in a different order of an object, but in memory, it doesn't matter for an object because it's a map, right? So you might have different syntaxes or different text files that leads to the same memory representation. Then the other way around, you have a serialization specification. And then, of course, that might serialize to a document that differs from the original one, right? Because you might output the keys in a different order, or you might have a canonical serializations for numbers, right? You might have, for example, the number 004 in an input document that gets parsed as an int 4. And then when you serialize it back, you're just going to write 4. Without the leading zeros, right? So there might be an N-to-1 mapping for parsing. And when you serialize back, there's a canonical way to serialize typically, and that needs to be specified. And finally, a test suite for people to try out their parsers, right? So this is the best you can ever hope. Of course, it costs a lot of money to do these things, all the resources that go into writing these documents. And this is why it's typically done in standardization committees. W3C, for example, if you look at XML, there are documents for the info set, there is a document for the serialization, and so on and so on, right? So this is just so you get the landscape, but really, the most important part is to have a very, very tidy representation in your brain of all the levels. So really try to take a snapshot of that and to remember these layers. For whom is that clear? Right, very good. Then I'm going to give you a general part on the type system. First, I have to say there's XML, there's JSON, but even then there's many schema languages. There's XML schema, there's schematron, there's RelaxNG, there's JSON schema, and so on and so on. It's likely you will see many others. For example, who knows protocol buffers in them, right? So that's also, in a way, a schema language. A Java class can also be seen as a schema language if you want. There are ways to map the Java classes to schemas. So it sounds complicated, right? So many different technologies. But the good news is it turns out they all look really the same in terms of the type system. And this is why I would like to give you a very general overview of how these things work. First, almost all of these technologies and systems distinguish between atomic types and structured types. That shouldn't be new to you. There's objects and arrays on the one side, and there's strings, numbers, booleans, nulls on the other side, right? So this distinction between atomic types and structured types is common to almost all of these technologies, right? It also has to do with the first normal form, the way that you restrict the leaves of your tree, so the values to be atomic types. What I said is silly because the leaves are anyway always atomic, but what I mean, the values in your table, if you're in the first normal form, should be atomic, and if you're not in the first normal form, you can nest. For whom is that clear, this distinction? Right? Okay. Then the atomic types, it's typically a restaurant menu. Just like when you go to the Mensa or to restaurants, there's a different menu everywhere, but in the end, it's more or less the same food, right? That the same choices overall of food. We're all humans. And so it's the same with atomic types. You will see different types, but again, they're more or less the same. They might have different names. They might have, so for example, there are strings. Well, you're computer scientists, so I think I can just move on, right? So strings is one of them. We have the numbers. So the typical numbers we have are the integer fixed size types. So 8, 16, 32, or 64 bytes, right? In Java, they're called byte short, int long. It turns out that that's also the names in XML for the type and also in JSON. Even now, we love the 64 bits. You heard of Gangnam Style, right? That's the video that broke the YouTube counter because they had a 32-bit counter and it was even signed. So it broke at 2 billion, and they had, just because of Gangnam Style, they had to move to 64 bits. And now they have 64-bit counters in YouTube. Okay, so there's this. Then we have fixed point decimals. So fixed point decimals is basically a bit similar to an integer, except that you have a dot at a fixed position in there, right? That's fixed point decimals. So all you need to say for that type is which precision you have, how many digits, and where do you put the decimal period. That's called the scale, right? It can be arbitrarily long, right? It can be also inefficient. So think of libraries that MATLAB or Maple, so these kind of mathematical libraries that can really grow to very large precision, very large numbers. So this is called fixed point, and they are very popular in database systems, can be very useful, but it's not very efficient to compute. So because it's not very efficient, we also have the floating point decimals that are a standard called EE754, known very often in many languages as float and double. It's a fixed 32-bit or 64-bit representations. It is so standardized that the CPUs efficiently deal with this, right? Maybe less than integers, but still they have, in hardware, you have this all hard-coded, right? You just have a limited precision of 7 digits or 15 digits roughly in base 10 when you use them. But you can see the powers of 10 you get are really good. I just jumped that slide here to say you that you can also not specify a precision and scale and just say, okay, arbitrary. Absolutely any decimal number, that's the mathematical set, any decimal number. Okay, so fixed point decimals and floating point decimals where you basically have the scientific notation, right? For whom is that clear? Right? You're computer scientists, so I assume all of that is clear. Okay, Booleans, I'm just moving on, right? Dates and times, it's the underestimated part of many systems. That's often an afterthought in terms of the type system. For example, JSON doesn't have in the syntax dates and times, right? It was added later in the schemas. But when you are in a company, in an enterprise environment, they're everywhere. So it needs to be also done cleanly. And fortunately, we have standards for that. It's called ISO 8601, if you want to look this one up. So we can model dates after the Gregorian calendar. There's also systems that handle other calendars because there's also other calendars. Then you have the times with hours, minutes, and seconds. Typically, you can go to milli or microseconds in many systems. So you can go after the decimal dot. Then we have also timestamps where you have the entire spectrum of values from a year, month, date, all the way to, oh, I went too far, to microseconds. And as you know, in terms of storage, you can store it as the number of milliseconds since January 1st, 1970, right? Which is a way of commonly doing that, right? So you can store it very efficiently, but the system will have the user-friendly representation and still be able to tell you what that date is. And also it can parse a date into that number of milliseconds. Not all date times can be done in this way because there are some of them that might, there's the time zones basically that make it complex. There might be also a time zone in addition that needs to be preserved. Sometimes you might also not have any time zone and that makes it even more complex because that's kind of an uncertainty about the exact timestamp within a 44 or even 46-hour window that might be. So anyway, what I'm saying is that it's complex, but fortunately we have a standard for writing them in JSON or XML. So that's the good news, right? That's ISO 8601. Then we have time intervals that you can also store as values. You can say, for example, 2 years and 4 months or 3 hours and 14 minutes. Can anybody tell me why I put that scary black line here between month and day? As a word of warning. How many days are there in a month? A variable number, exactly. So this is why you need to be careful. If you say 2 months and 1 day, then you don't really know, right? So be careful about that separation. All of the others are unambiguous. It's 12 months in a year. We have, did you know it's called the sexagesimal system, the 60 minutes in an hour and 60 seconds in a minute. So yeah, all right. Then we have binary data, typically as base 64 or in hexadecimal format. You can put it in JSON. and nulls, the JSON null. It also exists in XML. You also have a way of saying that an element has a null nil technically value. So these are the atomic types, and more or less, you're going to have them almost all in any system, right? They might have different names, but this is pretty much the menu that you have. There might be also others, for example, geographic locations. So there's that's not a complete list. Okay, who is with me? Okay, so I assume for computer scientists, there's not much new in there. There might be something that people are less aware of if you're not working in data. When you are working in databases, especially with syntax like XML and JSON, it's very important when you look at atomic types and atomic values that you distinguish between the typed value space and the lexical space. Who knows the difference? Awesome, then I'm going to explain. So the value space, it's kind of the actual value. For example, if you have the number 1, then this is the number 1, the mathematical number 1, right? But that mathematical number 1, you could define it, for example, as the class of all sets that are singletons, right? That would be kind of the abstraction of the number 1. So this is mathematical. But do you agree that all of these constitute perfectly valid representations of that number 1 if you write it down as a string? Who agrees with that? Right? This is all 1, right? And it has to do with the fact, first, it's because we are in the decimal system that gives us a representation. Not everybody has a decimal system. There's also civilizations that has base 20, for example, so it can also vary. We have the exponents and so on. So basically, there's many ways to represent it. The same for 4. That would be the mathematical concept of 4, the int 4, if you want, but these are all the representations. This here, this is technically text. It's a string, right? This is called a literal, or it is called a lexical value, right? You can use either one, right? It's a lexical value or it's a literal. And basically the idea is that you can parse this literal or this lexical value as a typed value. And that's what happens when you basically read that from JSON or XML, and then you have an int or a long or a float or a double or whatever that has the actual typed value in your system. For whom is that clear? Very good. So of course, that's true for any type. Booleans can also have multiple lexical values. I put here the PostgreSQL values of true. False might also have multiple lexical values. Of course, that depends on your system. Then we have dates. So when I told you the ISO 8601 standard, this is it. This is when you have a year, a dash, the month, a dash, and the day. This is the ISO 8601 standard. It's very good if you build a new system to stick to that standard, because too many people, when they build new system, just do ad hoc date representations, and the problem is that it's non-standard. Yes? Before? Oh, before BC. Oh, it might be that there would just be a minus sign in front. I will look that up. And then I'll tell you. I think there is a way. It's probably that you put a minus sign. Let me make a note. Yeah, that's a very good question. Since it's a standard, I'm pretty sure the committee thought of this possibility. All right, so that's for dates. That's still the same standard when you have also hours and so on. There's this capital T. It's arbitrary, but this is it, right? A capital T in the middle, and then you have the time zone at the end, like this, right? Who is with me? Very good. So this is ISO 8601. And there's also a standard for durations, 1 year, 2 months, 3 hours. It's capital P, it's always capital P. Then 1 year, 2 months, the same capital T, you know, that basically says it's now hours, 3 hours in here, right? That's also standardized. And not everybody uses that, of course, but if you don't know what to use, then it's a good idea to use the standard. Okay, it's very common also in many systems to have a subtype supertype relationship, but that you also know from programming languages, right? That you can have in Java supertypes, subtypes. And typically what we mean for subtypes and supertypes is that the subtypes value space is a subset of the supertypes value space. For example, integers are a subtype of decimal because every integer is a decimal. Okay. So this is for the atomic types. Now for the structured types, luckily it's also more or less the same. We typically have maps and lists. If you want to use the abstract data type terminology, it's maps and lists. And we've seen them already at many places, right? So maps, we've seen a record in PostgreSQL is a map, a JSON object, a Python dict is a map, a set of XML attributes is a map because there's only one. Duplicates are not allowed, right, in attributes. A data frame struct is a map. We'll see data frames a bit later. And then we have lists. A JSON array is a list. An XML element is a list because the children within an element are ordered. So it's also a list and they can also be repeated. A data frame array is a list. The PostgreSQL array type is a list and so on, right? For whom is that clear? Right? So again, you've seen that, right? Maps and lists. But of course, database people don't say maps and lists. They will rather say object and array, or maybe struct instead of object. But this is yeah, but it's the same, right? One more thing. So I'm giving you the high level view, right? It's very common when you have many values to say how many. And when we mean how many, we don't count like with integers. We say okay, exactly one. Or we say, okay, 0 or more, so any number of values, or we say 0 or 1, it's an optional value, either it's there, it's not there, or we say 1 or more, right? So this is called the cardinality constraints on some values. The common sign shouldn't surprise you. That's the same as in regular expressions, right? Who is not surprised by a star, a question mark plus, right? Okay, so that's familiar to you. So some systems use that. A common adjective, and here I have protocol buffers in mind that say required for exactly 1, repeated for 0 or more, optional for 0 or 1. So you see, even though it's called differently, the idea is the same, that you can restrict cardinality in this way, right? This scary slides I actually did by popular request because I was asked in a previous class a few years ago, could you please show us some correspondence table between systems so that we understand, you know, this idea? So I did that. So you have the ones you already know. There's Python in there. So you have here Python types, PostgreSQL. Who knows a bit PostgreSQL? Right. So there's the PostgreSQL type system. There is XML schema. That we will see, JSON, JSONic, but already that's the same. You probably notice these are exactly the same names, makes it easier. There is JSON schema. It's a bit more limited, as you can see, but I will tell you about it. And we have Spark SQL, we will see in a few weeks. But do you see the one thing you need to see here? The one thing you need to see is that it's more or less always the same types, they just have different names. This is what I want you to see, right? There's sometimes surprises. For example, a double in Python is actually called a float. So a float in many languages is 32 bits, but the Python float is actually 64 bits. So it's a double precision, right? And ints in Python are actually unlimited precision integers. It's not like a Java int that would be 32 bits, right? And you see objects corresponds to structs and to dicts, arrays corresponds to lists in Python and so on, right? Without knowing that by heart, who is comfortable seeing this table, right? It makes sense, right? Awesome. So this is really the correspondence. Some are missing in some systems and so on, but you know, this is just how it works. So see it a bit like, you know, this is Zurich Deutsch, Bern Deutsch, Walliser Deutsch, Auschwitz Deutsch, Basel Deutsch, and so on, right? It's just different dialects, but everybody understands each other. What that means is if you learn a new system, it will be a walk in the park. You just read the documentation and you will just see and figure out how they call their types. But again, it's a known territory. All right, who is with me? Very good. So now I'm going to move on after the type system, the generic type system. I'm going to move on to schema languages. I shortened the slides because there's good interaction in the lecture, and it's important for me to interact and answer questions. There's the textbook with the details of that. So I shortened the slides because there's no reason to spend too much time on this, right? It's also based on the experience of previous classes that I see when the lecture gets boring, then people start falling asleep and so on. So let's directly show you the highlights. What you have at the top of that slide is a JSON document. What you have at the bottom of that slide is a schema. What can you first notice about the schema? The first thing you notice? Yes? Yes, it is valid JSON, absolutely. It is absolutely valid JSON. It's also well-formed. It's well-formed and valid. And the reason you can say it's valid is that because you have a schema, right? So both of your statements are correct. It is well-formed and it is valid, right? Oh, did you mean, when you say well-formed, did you mean this one is well-formed or did you mean this one is well-formed? Ah, the schema. So yes. So basically what you've just said is, this is JSON. The schema is also a JSON document. And that is very often the case. A JSON, so here it's JSON. A JSON schema is also a JSON document. An XML schema is also an XML document. It's a very common thing to do, right? So you're absolutely correct. This is well-formed JSON. This is also well-formed JSON. And this is JSON that is valid with respect to this schema. Who agrees? Okay, awesome. So JSON was actually invented for simplicity and teaching. You see, it looks very much like the original document, but it just specifies some types here. Where do you pick the types from? Well, you pick them from this, right? And we'll have an even more complete list, but this is basically where you pick them from. Okay, so that's a flat example where it's in first normal form. All of the fields that are at the bottom are optional. So this is also valid, right? It's also valid against the schema because all the fields are optional. You can require them by adding a small exclamation mark in here, and then you say, okay, that means they have to be there, right? What you cannot have is extra keys, extra fields. So this would not be valid because it's not in this list right here. Who is with me? Right? Awesome. What you have at the bottom is called the compact JSON syntax. It means it's meant to be very compact, very easy to read. Okay. By the way, you noticed how I might use interchangeably key, field, property. It's really all the same, but depending on the technology used, people might say key, or they might say field, or they might say property, right? But we mean a JSON key. Okay, what else do we have? Oh, the list. So I'm giving you a more complete list of the type system. It's for XML schema, JSONic, JSON. It's all the same list, right? This is all standardized. It's a W3C standard, these types, except null. But all the others, it's a W3C standard. So if you use new systems, you rely on a standard that involved many people and many companies to get it right. Okay. What about structured types? Because I showed you how to write a schema with atomic types, all flat. For a structured type, well, you can say object array, right? These are also types. They are not atomic. And the document above is valid against the schema. Who agrees? Right? Okay. Name is an object, and theories is an array. But now you might say, okay, that's not very constraining, right? Because if I just say object, or if I just say array, there could be any object or any array in there. So can I constrain further what there is in this object or this array? And the answer is yes, you can. You can absolutely do it like this. So you can just nest here an object inside name and say last must be a string, first is required and must be a string. And for the array, you use exactly looking like the syntax, an array notation with just the name of the type in there. That means an array of strings. This is an array of strings, right? Who understands that syntax at the bottom, right? Okay. So it looks very much like the original document, and that's on purpose. That's pedagogical. You can also have nesting, so objects in arrays. So you can, for example, here have an array that contains a list of objects. That is in fact a nested table. Do you see the nested table here? This is a 2-column table with name and year that is nested in this object. Well, you can do it with this syntax. You just put the array type, and inside you have an object. And again, that's the skeleton of all of the objects in the array must all follow this. Right? So this is JSON. And if you don't want to restrict anything, just use the type item. Item means anything I don't care, right? So you can say an array of items, and then you can put whatever you want in there, right? So you basically can decide on how flexible you are with what you allow. Who is still with me? All right, I have a question there.
Just drop the item that is list, right? Like you don't need to specify as an item. If you go to slides before, a little bit more. Here, you can say just array instead of array effect.
You are correct. Absolutely. That is the same. Absolutely. You can say array or you can say item. It is the same. Yeah, absolutely. Well observed. Okay. Okay, and you can allow for any value like this. That would be heterogeneous, right? In that case, it's like a variant type. Yes? Yes, we do, just not in the compact syntax, but in the verbose syntax, you can do that. And actually, while I was saying that, I realized, no, you do have a way of a union with a vertical bar. If in the string you say a Boolean vertical bar, string, vertical bar, date, and so on, you can have a union, right? I just didn't say it. So yes, you can have unions, absolutely. And unions are common in all schema languages. You can have unions in XML schema, in JSON schema, in JSONs, and so on. Okay, so very good question. Okay. And speaking of which, I said there's a compact syntax and a verbose syntax. So the compact syntax handles 80% of the cases. But sometimes things are a bit too complex or you want to use advanced features, and then you need to switch to the more verbose syntax. Just so you see what it looks like this. It's just a bit more verbose. But why is that interesting? Because in the verbose syntax, you can specify that you accept more keys. For example, you have last and first, that are the two keys that you allow. But if you say closed false, so it's an open object type, then it's perfectly fine to have year or whatever other attributes you want. And then it's unconstrained, right? Only last and first are constrained, but any other attributes can have any value they want. This is called an open object type. Who is with me? Right? Very good. You don't have to worry too much about the verbose syntax. More the compact syntax is important. You just need to know that it exists and that you can do more things. So you see there's many things you can do with schema languages. So here I have a bit of a summary of the sort of things that a schema language gives you. So first, you can restrict specific values to a specific types. For example, you can say that you accept an array with integers, but you do not accept an array with anything else, like a string. So this would be valid, this would be invalid. A schema language typically has an implicit cast. For example, if you say foo is an integer, and here you have a string that is in fact a literal representing an integer, then when you annotate, you remember the annotating part, then you are going to cast it and have an actual integer as specified by the schema. So that schema languages do this. You can also require a value. You can say, I want foo to be there, and if foo is not there, that's invalid, right? So you can say, I want it to be valid or invalid, right? That you can specify in a schema. You can specify whether your object type is open or closed, so whether or not you allow for additional keys that are not in the schema. So you can say yes or no. That's your decision in the schema. What else can you do? You can specify default values. So you can say in the schema, if foo is not there, then it's true. And that means that when you annotate, you're going to add that default value right here. That also exists in PostgreSQL, by the way, and in SQL. You can also specify default values. And you can also have primary keys. So you could say, for example, when you have a nested table, which is an array of objects, you could say that foo is a primary key in the sense that you do not allow to have twice the same value in there, right? Who is with me? right? Looking at Zoom, because I think I see some animation on Zoom. So can you restrict a value to a specific range? For example, only positive integers? Yes, absolutely. You can do it in different ways, in fact. So you can do it first, if you look at the list that you have here, there is actually a type. You have positive, negative, non-negative, non-positive that are there. So this is one way to do it. But you can also specify intervals. So you can say, I accept all the integers between 42 and 84, for example, right? So you can also do this. This is very common to many schema languages. You can do it in JSON, you can do it in JSON schema, you can do it in XML schema, right? Okay, so that's a very good observation, and the answer is yes. Oh, not the right window. When I click to, I need to be on the PowerPoint window. You're welcome. Okay. So this is the sort of things you can do in pretty much any schema language. Now, back to an example. Did I tell you about the great language game? Right? It's a huge data set where people need to guess a language, and there are 16 million JSON objects in there. So when you have JSON objects that look structured, you basically, it's tempting to build a schema, and that would be the schema that you could have that would, against which the 16 million objects would be valid. Who agrees? Right? You see hex binary here as an example. That is a sequence of base 16 numbers. Okay, and a date. You see ISO 8601. There's even a date there. Okay, so that's an example, and that validates 16 million objects. This is the value. You rarely validate only a single object. You typically validate them in millions or billions. Do you remember this document? Can you try in your head to figure out the JSON schema for these documents? Just in your head, as an example. Who has it? Who had this or similar? Yeah, very good. So you see, it looks very similar, right? So I even was conservative and required A, B, and C. I require foo, but not bar. Bar is optional, so no exclamation mark. Long is arbitrary. I could have said int or integer or decimal or double or anything, right? But this is the idea, right? So this should be the intuition. And again, JSON was designed for teaching, so it's really meant to be very close to the original document, at least the compact syntax. Okay, all good with JSON? Okay. It's available in JSONic. I will show you later how you can use JSON to specify schemas in JSONic and then validate JSON within your Jupyter notebooks. Okay, I'm looking at the time, and I see that there's 2 more minutes. So I think I will not start with JSON schema. JSON schema is a bit more popular. It's well known, a bit more verbose, and I will just show you, but you will see it's pretty much the same. It's just that the syntax is different, but it does the same things. Any questions? I do not see raise hand. Yes, over there.
Type of variable is like an array, any sort of an array, and I just specify like empty square braces. Would that work?
Oh, empty square braces. No, you need to specify a type, I think, in JSON. You really need to do, even if it's item, right? Yeah. Okay, good question too. All right, then I will let you go. Enjoy the exercise sessions, and I'll see you next Tuesday where we finish validation. Thank you.